Hello, everyone. Thank you, JR. Hello, everyone. It's a really distinct honor and a great pleasure to welcome Professor John Preskill of Caltech for the CUbit Seminar today. John is really a pioneering figure in quantum information science, a teacher for many, many of us. And John got his PhD from Steven Weinberg in 1980 in particle physics, okay? Wrote many papers, 7 with Frank Kowalczyk. And then he decided to move on to the quantum information science in the 1990s. I remember when I went to Caltech to be a postdoc, John Preskill had a center, quantum center there. That was probably the first quantum information center at Caltech. And he was collaborating with Jeff Kimball, and it was the first time I learned that people in nonlinear optics talking about phase shifts in photons and so on, it can turn into a gate. That was where the start of the quantum information science. You can use the gate information, the gate knowledge, or gate way to think about nonlinear optics, atomic physics, and so on. So it's a very exciting time at the time, and John has been the director of the Institute of Quantum Information and Matter since 2000. It's akin to a PFC center at Jella. He's a Richard Feynman professor at Caltech right now. And as I mentioned earlier, his name is associated with some codes that you use for quantum computing, GKP codes. And he has written some of the early lecture notes, which serves as textbooks for quantum. If you want to learn about a quantum computer, you'll go look at John Preskill's notes from 1990s. And he continued to serve on many different advisory boards, national committees for quantum information. And he's just an amazing figure. If you like to talk to him to get an intellectual excitement or something of a practical matter from theorists. Thank you, John. Please, the floor is yours. One fun fact. John has a Twitter account and has 130,000 followers. And just be careful when you talk to him, because sometimes whatever you say will show up on John's Twitter.
Only the good things. Well, thanks very much, June. It's really an honor to be in Boulder, one of the world's great centers for quantum science, where so many milestones of our field have been achieved over the decades. When June was at Caltech in the 1990s, in the period he referred to, I was undergoing kind of a career transition. As he said, I started my career doing theoretical particle physics and early universe cosmology. But I don't really feel that what I'm doing now is so different from what I was doing earlier in my career. Now I work on quantum information science, and the way I look at it, quantum information science is the beginning of the exploration of a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. It's different from the short distance frontier we explore in particle physics or the long distance frontier of cosmology, but like those, it's very fundamental and exciting. We are now developing and perfecting the tools to create and precisely control very complex states of matter, states of many particles that are profoundly entangled, so complex that we can't simulate them with our most powerful existing supercomputers or understand their behavior very well with existing theoretical ideas, and that opens new opportunities for fundamental discovery. Our conviction that this frontier is fruitful to explore rests to a large extent on 2 central ideas: quantum complexity, our reasons for thinking that quantum computing will be powerful, and quantum error correction, which is our basis for believing that we can scale up quantum computers to large systems that can solve very hard problems. And both of those ideas rest on a fundamental underlying concept, what we call quantum entanglement. That's the word we use for the characteristic correlations among parts of a quantum system that are different from the correlations we normally encounter. You might think about it this way. Imagine a book which is many pages long. Let's say it's 100 pages. And if it's a conventional book written in bits, every time you read one of the 100 pages, you learn 1% of the information content of the book. And after you've read every one of the pages, one at a time, you know everything that's in the book. But contrast that with a quantum book. It's written in qubits, the quantum analog of bits, and the pages are very highly entangled with one another. For this highly entangled quantum book, when you look at a single page, you see only random gibberish. And even after you've read all of the pages, one at a time, you know very little of the information content in the book. And that's because in the quantum book, the information doesn't reside in individual pages. It's encoded almost entirely in the correlations among the pages. So if you want to read the book, you need to make a collective observation on many pages at once. That's the key principle of quantum entanglement. There can be a lot of information encoded in a system, but when you look at the parts one at a time, you can't access that information. Now, what's so interesting about quantum entanglement is that a highly entangled system, let's say hundreds of atoms, which are in a highly entangled state, is extremely complex to describe in terms of ordinary classical information. The quantum system speaks a different language than what we understand and our classical computers understand. So if I wanted to write down a complete description of a highly entangled state of a few hundred qubits in terms of bits, describing all of the correlations among those qubits, I'd have to write down more bits than the number of atoms in the visible universe. So it'll never be possible to write such a description down, even in principle. Now that in itself doesn't necessarily mean that we can do interesting things with this highly entangled state of many qubits. But we have some reasons for thinking that by processing entangled states of many qubits, we can do interesting things. One reason for that is that we know of problems which we believe are hard for conventional computers, but which theoretically quantum computers can solve efficiently. The best known example of that is the problem of finding the prime factors of a large composite integer. And the reason we think factoring is a hard problem is very smart people have been trying for decades to come up with better factoring algorithms. And still, the best algorithms we have running on conventional computers have a runtime which increases faster than any power of the number of bits in the number we wish to factor. There are also arguments from the theoretical computer scientists which indicate that I can do a quantum computation of modest size, acting on qubits, and then measure all the qubits, and that in doing so, I am sampling from a probability distribution that I can't sample from efficiently by any classical means. Excuse me. Most tellingly, we just don't know how to simulate in general with a classical computer what a quantum computer does efficiently. And that's not for lack of trying. Physicists and chemists have been trying for decades to come up with better algorithms for simulating highly entangled states of many particles. And still, the best algorithms that we have running on classical computers have a runtime in the hardest instances, which increases exponentially with the number of qubits. So we have reasons for thinking that quantum computing is in some sense more powerful than conventional computing, but we shouldn't think of a quantum computer as having unlimited power. In particular, we don't expect that quantum computers will be able to find the exact solutions to the hardest instances of combinatorial optimization problems. But we do think that there's a non-trivial classification of problems, that there are problems which are classically hard and quantumly easy, too hard to solve with reasonable resources for conventional computers, but easy to solve with quantum computers. So it's a compelling question to understand better what are these problems, which are classically hard and quantumly easy. And we've learned a lot about that in the past 25 years or so. I think we still have a great deal more to learn. and we will understand the capability of quantum computers better as we experiment more and more with quantum computers. But if you're a physicist, there's a natural place to look for where quantum advantage will occur, because we expect that with a quantum computer, we'll be able to efficiently simulate any process that occurs in nature. And we don't think that's true of conventional computers, which can't efficiently simulate very highly entangled matter. So with quantum computers, we expect to be able to go farther in exploring the properties of complex molecules and highly correlated materials. And we should also be able to explore fundamental physics in new ways. For example, by simulating collisions of high-energy particles, or the quantum behavior of a black hole, or the behavior of the early universe right after the Big Bang. It's not a new idea that quantum computers can be used for this purpose of simulating quantum processes. It was articulated over 40 years ago by Richard Feynman and Yuri Manin. And we're just now getting to the point where quantum computers are capable of doing interesting things. So evidently, building quantum computers is hard. What makes it hard is we want a quantum computing device to satisfy some criteria which are barely compatible with one another. On the one hand, we want the qubits to interact strongly with one another so we can efficiently process the information encoded by the qubits. We don't want the qubits to interact with the environment, which can cause a quantum computer to crash. But we do want to be able to control the quantum system from the outside and eventually to read out the qubits to find the answer to some hard computational problem. And it's quite hard to build a platform that simultaneously satisfies these desiderata. It's only after decades of technical progress that we've gotten as far as we have. So why do I say it's important for the qubits to not interact with the environment? And that's because of a fundamental difference between conventional information and quantum information, namely that we can't observe a quantum state without disturbing it in some uncontrollable way. That's not true of ordinary bits. We can observe a bit to see whether it's a 0 or a 1 without flipping the bit, but quantum information is more delicate, and when we observe it, we disturb it. And even if we don't observe it ourselves, if information which resides in a quantum computer leaks to the outside world, where in principle it could be measured, then the encoded quantum information becomes damaged. That's the phenomenon we call decoherence. It's really the enemy of the quantum computer. And if we want to resist decoherence, we have to prevent the information that's being processed from leaking to the outside world. And that's really hard to do because our hardware isn't perfect. But we've understood in principle how to isolate a quantum computer extremely well, even though its hardware is imperfect, using the idea we call quantum error correction. And the essence of the idea is that if I want to protect a quantum state from damage, then I should encode it in a very highly entangled state, in a very non-local way. And then the environment interacts with the quantum computer, with our quantum system locally, in effect reading one page at a time, in analogy to that book I spoke of earlier. But it can't see the encoded information by looking at a single part at a time. So the information remains concealed and therefore isn't irreversibly damaged. And we've understood, in principle, how to efficiently process quantum information that's encoded in this very highly entangled form. And that's how we expect the large-scale quantum computers of the future will operate. So where's the hardware now? There are a number of different approaches to building quantum hardware, which are under development and steadily advancing. And it's important at this stage that we pursue a variety of different hardware approaches, because we don't have a clear idea at this stage of what technology has the best long-term prospects for scaling up to large systems. And it might be some hybrid of different technologies, which turns out to serve our needs, or different technologies might find different niches. A qubit can be instantiated in a variety of ways. It could, for example, be carried by the spin or magnetic field of a single electron, or the phase or polarization of a single photon, or the internal state of a single atom, which is, say, either in its ground state or some long-lived excited state. And those are all very remarkable encodings because the information is carried by these very fundamental single quantum systems, and yet we've learned, thanks to decades of technical advances, to control these systems quite well, to a large extent, thanks to work that was done at Boulder. The information can also be encoded in a more complicated system like a superconducting circuit that conducts electricity without resistance at very low temperature. That's also a very remarkable encoding because in this case the information is carried by the collective motion of billions of pairs of electrons, but we can control the qubit as though it were a single atom. So it's useful to have a word to describe the current status of quantum technology. The word NISQ has caught on. It's an acronym which means noisy intermediate scale quantum. Intermediate scale to convey that we now have systems with a sufficient number of qubits, of order 100 or so, that are large enough that we can't, by brute force, simulate what the quantum system does with our most powerful existing conventional computers, but noisy to remind us that these systems are not error-corrected, and the noise is a serious limitation on their computational power, a limitation on how large a computation we can carry out successfully. Now, for physicists, NISQ is exciting. It means we have a new tool for exploring the physics of many entangled particles in a regime that we never had access to before. And it's possible that NISQ technology will have practical applications of broader interest, but we're not really sure about that yet. So we shouldn't think of NISQ, of quantum computing without error correction that we have today, as something that will change the world by itself. It's a step towards more powerful quantum technologies we're hoping to develop in the future. If we look ahead, we can envision applications of quantum computing to, say, problems in chemistry and material science, where if we had a perfect quantum computer with a few hundred physical qubits, we'd be able to solve problems that are beyond the reach of our most powerful conventional computers today. But the catch is that would be true if we had a perfect quantum computer that never makes mistakes, one with no noise. We don't have that now. In the quantum computers that currently exist, every time we perform an operation on a pair of qubits, the probability of making an error is a little bit less than 1%. And that's steadily improving. So we might, in a few years, have multi-qubit devices where the probability of error per gate is 0.1%. But to run these applications, we would like to have an error rate per gate which is orders of magnitude better. 10 to the minus 10, 10 to the minus 12. There's an enormous gap between, well, where we'll be in a few years with an error rate of 10 to the minus 3, where we want to go, an error rate of, say, 10 to the minus 12. And we think it's possible to cross that chasm using quantum error correction. But quantum error correction has a significant overhead cost. So in order to bring the error rate down to the regime that we'll need, we might need thousands of physical qubits to encode each protected logical qubit to run applications of sufficient scale. And so that would mean a device with millions of physical qubits. And that's a long way from where we're likely to be in the next few years with devices with hundreds of physical qubits. And crossing that chasm will take a lot of time and effort. Now, meanwhile, it's important to continue to try to improve those gate error rates. One way of doing so might be different qubit designs which have some robustness against error. And here are a few that I'm partial to, different ways of realizing qubits that people are starting to explore. And I won't explain them, but they all have in common that to some degree the resistance to error is built into the hardware itself. rather than accomplished by software on top of the hardware. And all these ideas are in their early stages, and we don't know how well they'll pan out. But it's important to try, because much lower physical gate error rates would increase the power of quantum computing in the NISQ era, and it will also significantly lower the overhead cost in the error-corrected quantum computers we expect to build in the future. So there are really two big open questions confronting quantum computing technology. How are we going to scale up to quantum computing systems that can really solve hard problems? And once we do so, what are the most important applications to run on those machines for science and for industry? And I really consider both questions to be wide open. I think we have a lot of basic research and investment to make before we'll have really satisfying answers. Now that said, I think this is a really exciting time, and that remarkable developments are likely to occur in the next few years. I think we'll see encouraging progress towards realizing error-corrected quantum computing in real devices. So we'll be on the path towards those scalable devices that we'll need. And meanwhile, with the quantum computers and the programmable quantum simulators that we now have, we'll be able to explore the properties of highly entangled matter, in particular its dynamics, in ways that we never could before, and that will enable new scientific insights. And it's also noteworthy that a convergence is occurring between the physics of many interacting particles and quantum measurement science. Increasingly in the future, we'll be able to use entangled states of many particles as measurement probes to achieve greater sensitivity, and steps in that direction will, I think, be exciting over the next few years. Now I'm going to switch gears a little bit, and I want to talk about some of the progress that we're making in understanding how to learn about and describe and predict properties of very complex quantum systems. Understanding quantum systems of many qubits is a huge challenge. We're talking about systems that have a Hilbert space of enormous size that we really can't imagine, a dimension of 2 to the 100, say, for a 100 qubit system. Excuse me. We are, after all, classical beings, but we live in a quantum world. And our classical nature can sometimes impede our ability to interact with, learn from, and understand the underlying quantum reality. But we're physicists, so what we like to do is to find relatively simple classical models of the systems we encounter in the laboratory, and then use those models to make predictions about systems that we haven't encountered in the lab before. And that's a task which can be better facilitated if we use tools from machine learning. For example, we might want to make use of the reams of data that we've already collected about properties of chemical compounds and highly correlated materials, and from that data, generalize to make predictions about quantum materials that we haven't synthesized before. We have the capability now of realizing new phases of matter, either equilibrium phases or phases far from equilibrium, unlike any that we've seen before. But how are we going to recognize when something qualitatively new has been corrected in a complex quantum system? Already, experimentalists are increasingly using the tools of reinforcement learning to more precisely prepare target quantum states using limited experimental tools. And as mentioned, quantum metrology offers the opportunity to better, more accurately sense very weak signals in very noisy data, and machine learning can help with that task as well. So something we've been thinking about in our group the last couple of years is how can we make more efficient the task of learning about quantum states, observables, and processes. And in all three cases, the learning protocol has 3 stages. We make measurements of quantum systems in the lab. We collect training data. From that, we create some classical model that describes the data. And then we try to use that model to predict properties for new systems that we haven't yet encountered during training. So what we'd like to know is how much training data do we really need to make good predictions? And how much classical processing do we need to construct our model and to use it to make predictions? And what's really experimentally feasible, either now or in the near or foreseeable future with realistic experimental methods? And I've worked on this with a number of collaborators that I've listed, especially Robert Huang, a former Caltech student, and Richard Kung, a former Caltech postdoc. And what I know about machine learning, I learned from my collaborators, and all our technical results really are to the credit of these collaborators. So let's talk about what it means to learn a many-qubit quantum state. So let's suppose that we have access to some unknown quantum state of n qubits. N is a big number. And we can repeatedly prepare that state. So we have access to multiple copies. It might be prepared by a quantum computer or some quantum simulator or some procedure we carry out in the lab. And I could consider more general things, but let's suppose that each time I receive another copy, I measure it in some way. And let's also suppose that those measurements are non-adaptive. That is, the measurement I perform on each copy is not conditioned on outcomes of measurements I performed on earlier copies. So I'm not allowing collective measurements across the copies or to use what I've already learned to decide what to measure next. Our goal is to learn the state, which means I should be able to predict the expectation value in some observable of choice of that unknown state. Now, we can't expect to learn everything about an n-qubit quantum state when n is large. It lives in a Hilbert space, which is 2 to the n dimensional. The number of experiments I would need to do to completely characterize the state is exponential in n. The amount of memory I need to store that description in a classical memory is exponential. The amount of processing I would need to do to make predictions using that description is also exponential in n. So we lower our sights a little bit, and we say we'll be satisfied to be able to predict with a small error and with a high probability of success the expectation values of all of the observables in some restricted family. That's our goal. And we might also want to learn nonlinear properties of the unknown quantum state, like Renyi entropies. You can think of those as expectation values of observables that act on several copies of the state rather than a single copy. But I'd like to be able to predict those based on my single copy measurements. So we've developed a scheme we call classical shadows of quantum state, which is a protocol for accomplishing this task. And the general form of this protocol goes like this. It's defined by some ensemble of unitary transformations. And for each copy that I have access to, I sample one of these unitaries and I apply it to the state, and then I measure all the qubits in the standard basis. So for each n qubit quantum state, I acquire a string of n bits. And then if I apply the inverse of the unitary transformation to that bit string, that provides me with a snapshot of the state. If I want this to be a practical protocol, then I want all the unitaries in the ensemble to be ones I can really perform in the lab and ones which I can describe succinctly using classical language. And now there are 2 sources of randomness in this procedure. There's the randomness of the choice of the unitary that I apply and the randomness of the quantum measurement process. And if I average over both those sources of randomness, that defines some map on the quantum state, which takes the unknown state rho to some other state. And if the unitaries that I've chosen from have the property of making my measurements tomographically complete, if they completely characterize the state, then that map will be an invertible map. Now, its inverse is not a physical operation I can perform in the laboratory, but it doesn't need to be. I don't want to perform that inverse of the map in the lab, I want to perform it on classical data that I've stored in a classical memory. And then if I apply the inverse of the map to the snapshot, I'll call that an inverted snapshot, then when I average over the choice of unitary and the measurement outcomes, I can recover the unknown state row. So the inverted snapshots provide an unbiased estimator for the unknown quantum state. If there's some observable whose expectation value I want to estimate, what I can do is for each one of the inverted snapshots, I evaluate the trace of the inverted snapshot times the observable, and then when I average over many runs of the protocol, that's guaranteed to converge on the expectation value of the observable that I want to know. But there are fluctuations in the estimator, and so we would like to know what's its variance and how likely is it that there's a large deviation away from the mean value. So let me give a particular example, which I've chosen because this is something that's experimentally feasible in today's quantum devices, for example, in ion traps or superconducting circuits. For each one of the qubits in each one of the n copies, I decide uniformly at random to measure one of the Pauli operators, the Pauli operator x, y, or z. So the snapshots are product states, a product of states which can be chosen from 6 possible states, the eigenstates with eigenvalue +1 or -1 of the 3 Pauli operators x, y, and z. To find the inverted snapshot, I have to invert the map defined by that random choice of measurement, and it turns out that qubit by qubit, the inverted snapshot is 3 times the projection onto the snapshot minus the identity. Now that's not a physical density operator. Physical density operators have eigenvalues which are between 0 and 1. This inverted snapshot for a single qubit has eigenvalues +2 and -1, but it's okay. When we average over many inverted snapshots, it will converge on the unknown state. So for this particular example, we can compute the variance of the estimator. We call it the square of the shadow norm, a norm we define for this purpose, and it can be related to the spectral norm of the operator, its maximum eigenvalue. But there's also a factor that depends on the weight of the observable, the number of qubits on which it acts non-trivially, and it's exponential in the weight. But if I'm interested in estimating observables that act on a fixed number of qubits, or sums of such observables which have a constant spectral norm, then this variance actually doesn't depend on the size of the system. It's independent of n. And so what that means is, let's say there are m observables, which all are such local observables with a bounded shadow norm, and I'd like to estimate them all simultaneously. Well, the number of copies that will suffice for that purpose, the number of copies I have to measure, increases only logarithmically with the number of properties that I'd like to estimate. And the reason it works that way is that if I do my estimation sensibly, then the probability of a large deviation away from the mean value is exponentially small in the amount of deviation. So I can estimate many observables with a guarantee that with high probability, all of them are close to the mean. In fact, I can estimate all of the local observables, all of the observables which act on a constant number of qubits at once, with a total number of copies, each measured by this classical shadow protocol, which goes only logarithmically with the size of the system, the log of the number of qubits. So for example, I might be running a variational algorithm on a quantum computer where I'm trying to find a state which has the low value of the expectation of some local Hamiltonian. And that Hamiltonian is a sum of local terms, each acting on a constant number of qubits, with maybe a polynomial in n number of terms. And then I can measure all of those terms simultaneously with a small error by measuring a number of copies of the state, which only goes logarithmically with the size, with the number of qubits. A nice thing about this procedure is that at the time I make the measurements, I don't need to know what observables I'm going to want to predict. So I can measure first and ask questions later. And in fact, many of the applications that have been carried out using classical shadows in the last couple of years have been done by reanalyzing data that was originally taken with a different purpose in mind. Now, the procedure I described does kind of a local scrambling of the state. We rotate the Pauli basis, and then we measure each one of the qubits. And that's enough to give us access to all the local observables. If I could globally scramble the state, then I would get access to some global observables. For example, the overlap of the unknown state with some target quantum state that I'm hoping to prepare. But to do that global scrambling requires a deeper circuit with more steps. In fact, the number of steps required goes roughly linearly in and the number of qubits. And that's not so practical today. If I have a system with 100 qubits and I have to do about 100 steps of a computation with the noisy computers we have today, I can't really get an adequate signal to noise. But we can also consider an intermediate case where I apply an operation of some constant depth, and as that depth increases, I'm getting access to observables of higher and higher weight. So I might consider an analog simulator which has its native, strongly chaotic dynamics, and if I want to get access to observables in that state, I can let it evolve for some amount of time and then measure all the qubits. And as I let it evolve for a longer time, I get access to operators that are higher and higher weight, act on more and more qubits. But the catch is that the inverse of the evolution that I have to compute in order to find the inverse of the map gets harder and harder as I increase that depth. Now, with quantum computers today, they're not perfect. They're noisy when we make measurements. But there's some pretty nice robustness to noise in this classical shadow protocol. In fact, the fact that it's a randomized measurement procedure simplifies the structure of the noise, and that makes it easier to characterize. And then I can include a description of the noise in the inversion of the map and obtain, again, an unbiased estimator. But there will be some sampling error in the estimation of the noise, and that will contribute to the variance of the estimator. So if I want to accurately measure all the local observables in the noisy case, I'll have to measure more copies than I would in the noiseless case, but not necessarily so many more copies. All right, so I've described what it means to learn a quantum state. The state can be arbitrary. It could be an extremely complex state, and I can't predict everything about it. But I can predict the expectations of some restricted class of input observables after measuring a modest number of copies of the state, like, for example, all the local observables. So what does it mean to learn an observable? So let's suppose we have some box or procedure which performs a measurement. We don't know exactly what it's doing. We'd like to learn the observable by taking quantum data. Well, we can't expect to learn everything about the observable. That would be too much to ask. But what we can do is predict the expectation value of that observable in some restricted class of input quantum states. And a nice way to formalize the problem is to suppose there's some probability distribution on the input states. And then my goal is to learn a function of states which approximates the expectation value of the unknown observable in the state with some small error when we average over the input states according to this distribution on input states that we define. So again, we could ask, for that task of learning an observable defined in that way, how much training data do we need to do it well? how much classical processing is required to make good predictions. And there's a nice feature that leads to a good answer, which is that as long as the distribution on input states is sufficiently smooth, it suffices to learn an approximation to the unknown observable, which is truncated, in which I keep only its low-weight contribution. So let's imagine the unknown observable is expanded in terms of a complete basis for operators, all the Pauli operators. There are 4 to the n of them, acting on n qubits. But suppose I throw away all the coefficients of the high-weight operators that act on many qubits, I just set them to 0. That truncated operator will approximate well the complete operator when I average over a smooth distribution of states and compute expectation values. Furthermore, in that truncated version of the observable, the description that I need to learn is pretty sparse. The number of non-zero coefficients I need to get a good approximation is not so many, and that makes it possible to learn the observable efficiently. Furthermore, because of this truncation, if I want to estimate the expectation value of some input observable, all I need to know about that observable are its reduced density operators on small numbers of qubits. I can throw away the parts of the state where I need to retain, well, basically I can trace out all the qubits except for a few and keep those reduced density operators for all possible choices of those few qubits, and that's enough to predict the expectation value with a small average error. And we proved this rigorously in the case of what we call a flat distribution, which means the probability distribution on input states is left invariant if we locally twirl any one of the qubits. So it turns out that the error that we make when we truncate the observable falls off exponentially with the level of truncation. So if I only keep observables in the truncated expansion, which act on up to k qubits at once, then I'm making an error which is exponentially small in k. So if I want to have a small average error, I only have to keep k going like log of 1 over epsilon, where epsilon is the accuracy that I want to achieve. And now the task is very efficient. The number of copies we need to measure, again, just scales like log of the total number of qubits. And the computational cost of learning and predicting is also reasonable. It's linear in the number of samples that we measured, and it goes like n choose k, which is a polynomial in the system size n if I'm trying to achieve some constant accuracy. So we can learn observables too. So what does it mean to learn a process? Well, so far I've described how to learn a state. It can be any state, but our protocol doesn't try to learn everything about it. It learns, say, the local observables. And I talked about what it means to learn an observable. Well, we don't learn everything about it, but we learn how to predict with a small average error over some nice smooth distribution on quantum states. So now when I say learn a process, what I mean is that from the data I collect in quantum experiments, I'd like to be able to predict the expectation values of local observables in the output state with a small error when I average over some smooth distribution on input states. And that's something that we pretty much already know how to do if we can learn observables. We can think about this task in the following way, that what we're trying to learn is this quantity. We're trying to find a function on states and observables which matches with a small error the expectation value of the observable in the output from the process, which I've called E. And you can think of this in terms of the Heisenberg picture instead of the Schrödinger picture. We can think of the dual Heisenberg picture version of the process acting on the observable. And then we're trying to learn an unknown observable in some input state. And so the task of learning that unknown observable can be accomplished by the protocol I just described for learning unknown observables. And the training data that we need for this task can be obtained by measuring the classical shadows on the outputs, because that's enough to characterize all the local observables in the output. And it turns out that during training, all we need for input states are product states. And that's because we really only need the few qubit marginal density operators to make good predictions. So we can learn observables efficiently too, learn processes as well as observables. So there are a couple of things about that seem surprising. We can efficiently learn the process even if it's exponentially complex. It could be something that took a quantum computer the age of the universe or longer to carry out, but we can learn the process efficiently in the limited sense I described. Namely, that we can make accurate predictions for output local observables, not for all possible inputs, but averaged over a smooth distribution of input states. Another thing that's surprising is that although during training we only input product states, our distribution can have support on entangled states, and we can predict well for highly entangled states as well. So in some cases, the classical machine learning model, making use of data from quantum experiments, can predict the outcome of a process much faster than the time needed to run the process itself in the lab, once we have enough training data, and we don't need so much. So these rigorous results apply to the average error. You could ask, well, if I pick some particular structured states, how well does it work? We've done a number of numerical experiments to check how well it works. For example, this is from experiments with quantum spin chains with up to 50 spins, which could be either translation invariant or disordered spin chains. And in the lower left, this shows how, if our goal is to predict the expectation values of the Pauli operator Z acting on each one of, say, 50 qubits, to predict them all accurately, the amount of, how the error goes as we increase the amount of training data follows a nice power law, which is actually a bit better than our rigorous results can guarantee. And in the upper right, we consider increasing the evolution time. Here time is measured in units where the energy scale of this Hamiltonian is 1. And as we go up to an evolution time of 1,000,000, our prediction performance is almost constant. So the evolution time doesn't matter very much. And on the lower right, we show how the prediction performance behaves as we increase the number of spins from 10 to 50, and the dependence on the system side is very mild. Actually, these plots were created for the case where we input product states different from those used during training, but it also works for entangled states. So here's an example where half of the qubits are in an entangled state, cat state or G8Z state, and the rest are in a product state. And then here are the expectation values of Pauli operator Z, shown for each one of the 50 qubits for 4 different times. And when we get up to a time of 1,000,000, the dependence of the expectation value on position is something pretty complicated, but the ML predicts it very well. So how can we use these observations about how to improve the efficiency of learning states, observables, and processes to learn new things about physics? Well, we thought about several aspects of that. One is the task of learning local properties of ground states of quantum systems. Now, let's suppose there's some smoothly parameterized family of Hamiltonians, and during training we have access to the ground states of some Hamiltonians which are sampled from that ensemble of Hamiltonians. They're all gapped Hamiltonians. So we say all these ground states are in a single quantum phase of matter. Gap means there's a non-zero energy gap between the ground state energy and the first excited state energy. So during training, we're sampling representatives of some quantum phase of matter. And then our task after training is to predict properties like expectation values of local observables for other states that are in the same phase of matter, ground states of other Hamiltonians in that same family of gapped Hamiltonians. So our idea about how to do this is that during training, every time I give you a sample ground state, you immediately perform this random Pauli measurement to find its classical shadow. And then after training, we use classical machine learning to generalize the classical shadows to succinct classical descriptions of other quantum states in that same phase of matter from which we can infer the local observables. And we can show that this can be done efficiently, that the number of samples that you need and the amount of processing you need to do scale reasonably with the system size and the dimension of the parameter space for the Hamiltonians. Another task we've considered is classifying quantum phases of matter. So let's suppose that during training you have access to many qubit quantum states which are selected from either one of two phases, phase A and phase B. And during training, those states are labeled according to whether they belong to phase A or phase B. And then after training, I provide access to unlabeled states, and you're supposed to classify them according to whether they belong to phase A or phase B. So the idea in this case is that during prediction and training, when we acquire a state, we immediately measure it, do experimentally feasible measurements to find the classical shadow. And then the problem becomes, can we classify the classical shadows? And we show that that can be done efficiently. The procedure is kind of a standard one in learning theory. We define a map of the classical shadows as some high-dimensional feature space, and then we learn a classifying function in the feature space. So at the beginning of the protocol, we don't know what to measure to identify the phases, but the machine learning algorithm learns the function that identifies whether it's in phase A or phase B, and that instructs the physicists about how to think about the difference between the two phases. And although our rigorous theorem doesn't guarantee it will work, we've also seen that this method works well for unsupervised learning. So let's say you don't have access to labeled representatives of the two phases, but what you do instead is you take the classical shadow of sample states and then you map those to this high-dimensional feature space and then do a principal component analysis in that space. And you can see that states which are from different phases of matter are very cleanly separated from one another and easily distinguished by that principal component analysis. All right, so let me sum up. Broadly useful applications of quantum computing could still be a ways off. Quantum error correction is likely to be the key to getting there. But already the existing quantum platforms provide us with unprecedented opportunities for exploring exotic properties of quantum matter. I told you about classical shadows of quantum states. That provides a feasible procedure for converting a quantum state to a succinct classical description from which many properties can be derived. We can predict m properties with access to only order log m copies of the state. And furthermore, we don't have to know what properties we'll want to predict. At the time the measurements are made, we can measure first and ask questions later. And we saw how classical shadows can also be used to learn observables and learn unknown processes, even when those processes are extremely complex, under a restricted definition of what it means to learn the process. So that's an example of how, if we have access to data from quantum experiments and we use machine learning, we can solve some quantum problems that would just be too hard to solve if we didn't have access to data. So it's an exciting time for quantum science. We have the capability now of exploring highly entangled matter in ways that we never could before, and theoretical advances are providing us with better tools for learning about and predicting the properties of those complex quantum states. Thanks for listening.
Yes. Yeah.
Thanks for the nice talk, John. I still struggle with the classical shadows thing because there's sort of seems to violate the quantum no free lunch principle, that you can take a potentially complicated quantum state and distill it in an effective way to classical things. So what's the catch that exists there, or is there one?
So the question was, how did I get away with this? Is it a swindle? Well, the important point is that we didn't try to learn everything. And we had a certain protocol, and depending actually on how we structured that protocol, that choice of unitaries, it gives us access to some particular set of observables. And many things that physicists want to know, like correlation functions, expectation values of local observables, are things that we can learn just from the local structure of the state. We don't have to know about everything about the many-body entanglement. So the thing that's kind of cool is that we can learn many such properties highly efficiently.
Yeah. I have sort of firstly, that was an amazing talk, thanks. I have a related question. So there are a lot of numerical techniques that I guess you would say make the mistake of trying to actually solve for the exact quantum state as opposed to the sort of particular feature that you're interested in. And then there are also methods that allow you to sort of tunably add imprecision, so like matrix product states. And what I'm curious about is whether if I choose certain observables that are sort of very hard to simulate, so something like extremely non-local, can I do it here in a way that's more efficient than what I could do sort of numerically simulating the system? Or in other words, the problem's a little bit different, I guess, because in one case you're sort of numerically trying to simulate some process, whereas in this case you're trying to learn from the data. So maybe the question I should phrase differently. Can you learn better numerics based on sort of what your machine learning tells you? In other words, you get some network that sort of tells you how to invert your data and get some very abstract quantity that otherwise would be very difficult to simulate. Can you learn new ways of doing numerics based on sort of what the network has told you?
Yeah, so I think the question is about whether this provides us with tools for doing simulations more efficiently on classical computers, even when we don't have access to data in the laboratory.
Yes.
Not so much as far as we know. Like one idea we had was that maybe we could use this to do more efficient simulations of quantum dynamics, where we, without any access to data, but where the goal was to predict only the global observables at the end of the simulation, and so to sort of continuously update the classical shadow description until we have one, that's reasonably accurate at the final step. And that didn't seem to work. So I think the magic comes from the empowering access to data, and this is a very efficient way of generalizing that data to different situations.
John, can I ask really quick on the last point? Can I interpret this as if I have access to some experimental data, it's through classical machine learning, I can always come up with very powerful algorithm that basically as powerful as quantum algorithm to understand the quantum system. Is that what you're saying, or that's not what you're saying?
Well,
this is going back to the question of a quantum advantage.
Well, for this last statement about problems that are too hard to solve, to prove it, we can use a trick like this. We can encode in the ground state of some system with a local Hamiltonian the solution to a factoring problem, which we think is hard to solve classically. And then we can show that with, you can get access to that solution by taking the classical shadow of quantum states in the, that same family and generalizing them to the quantum state that gives you the answer to the factoring problem. So there was something that was classically hard in that state, and we were able to get it out by doing simple measurements and classical machine learning. That would be an example.
Yeah, thanks.
Mm-hmm.
Other questions? That one first.
Hi, thank you for the talk.
Thanks.
I had a quick question about a comment that you made earlier. You were saying that for this inversion map that you're using, that you needed it to be informationally complete, and that's sort of to allow you to distinguish between different quantum states uniquely. Have you thought about relaxing this condition whenever you're looking at an observable that you don't care about the exact quantum state, such as like purity?
I'm sorry, I couldn't hear the question very well. Could somebody repeat it, maybe?
I can just repeat it again.
Oh, okay.
Sorry.
I'll come closer.
So when you were talking about this map, this script M map, you were saying that you needed it to be informationally complete.
Yeah.
And this is sort of so that you can uniquely identify a quantum state whenever
Right.
you do it. Have you thought about relaxing this condition so that you don't actually want it to be informationally complete for estimating observables that don't need it? So like purity doesn't exactly need the state, but it's still like a 2-qubit observable.
Yeah, okay. The question is, I talked about this procedure finding a map defined by our measurement protocol on quantum states, and I said it was important that it be informationally complete so that we could invert the map, and that's how we acquired our unbiased estimator for the unknown state. So the question is, well, what if we consider a protocol in which those measurements are not informationally complete? And then we would be limited to defining a pseudo-inverse on some subspace of the quantum states for which such a pseudo-inverse made sense. And with the protocol, could the protocol be used then to make good predictions in that case? I actually haven't thought about that very much. I think in general it could fail, but there will be some class of observables for which it'll work, which depend on where that pseudo-inverse can be defined. But I have to think about it to give a more precise answer.
Thank you.
Perhaps one last question from Aaron.
Yeah, so I guess I was wondering, it looked like in this scrambling step you were always restricting your operations to Clifford's. Is that sort of an important restriction so that the inversion step is easy, or is there maybe some benefit to giving yourself access to non-Cliffords?
Well, the reason I like Clifford is that, well, it didn't matter so much in the case where I did these local observables. But I made this remark about globally scrambling the state. And what I had in mind in that case is doing Clifford circuits, which have sufficient depth to scramble the state almost linear in n. And the reason I like that is because we can simulate Clifford classically, then I know how to define the snapshots, which involve the inverse of the unitary applied to the data. I also mentioned a case which really wasn't Clifford. I mentioned it in passing. The case where we just do the chaotic dynamics determined by some many-body Hamiltonian for some fixed amount of time. That's not Clifford. And as a result, as I also mentioned, it becomes computationally quite demanding to find the snapshots and the inverted snapshots as you increase the evolution time. So, with Clifford, you can go further in scrambling the state and get access to higher weight observables more easily.
Cool, thanks.
If there's no more further questions, John will still be around tomorrow. And in fact, he has a whole day here. If you have questions, you can access, maybe talk to us, and I will make a connection for you. But other than that, let's thank John for an amazing talk.